This is my company. My motto is, and mission is to provide education in emerging technologies for free, right? Emerging technologies to masses for free or for very affordable rate, okay? And the objective is to share knowledge and achieve permanence in everyone's life. My company is official, with these institutions and companies. I offer training in IoT, in cloud computing, Kubernetes, big data, Python, predictive analytics, AI, deep learning, blockchain, cybersecurity. So I offer training in these areas, and I offer different aspects of vendor agnostic. I'm not trying to sell any product, or it's a one-time repeat policy. So if you enroll in my training, you can join one more time. We have expert teachers, so I've showed you the faculty list. We have a variety of courses, as I showed you, and emerging technologies like quantum computing is very hot today. A lot of new development happening every day. You hear news about it, and it's hands-on learning. It's hands-on. You don't have to worry about like it's all practical and applied. It's not theoretical, and it's the best value, right? I've taught thousands of students. These are my corporate. So you're most welcome. I will put this link in the chat, so you're most welcome to join the email list. I send out emails about my courses. Instructors, we have all these instructors. I'm a faculty at Cal State East Bay and at the San Jose State University, and also at Tier 2, Tier 3 schools in the Bay Area. So these are the faculty who teach during my courses. Majority of courses during COVID is taught by me and Sunil, but we have other faculty who join and teach the courses once in a while, okay? You'll find all the videos of my training. I appeared at NBC Bay Area, ACM. I continue to give training at ACM, some of the Open Data Science Conference. So you're most welcome to watch these. Right now, as I said earlier, the training is in online Zoom meeting, but I offer training at Embassy Suites in Santa Clara or in Seattle, right? And you can always contact me. You can send me an email, okay? So let's get started with our core training. So in general, quantum computing has been in news for quite a while. Okay, so quantum computing has been in news for quite a while, but the recent past, you are seeing a lot of breakthrough, right? You are seeing teleportation, news in teleportation happening out there. There is a lot of activities in quantum supremacy. Yesterday, Google found a clock, bistable clock with no energy consumption, right? So Google was able to demonstrate. I'll show you that demonstration later on, that they're able to change space and time without spending any energy, right? Same item can be in two places at the same time. Teleportation through their quantum annealer. We are able to see factorization. A lot of evidence of factorization, quantum random number generation, right? We are seeing a lot of those activities happening out there, where you are seeing quantum random number generation, and then using that to break the encryption, right? Way to break encryption. Optimization is quite popular, like optimizing, scheduling, mathematical programming type of applications, linear programming, dynamic programming, knapsack problems, those type of problems They have been in use for a while, and now you're seeing a lot of activity in this area. So these are a part of the theorems, like Shor's algorithm. We have um, Grover's algorithm, Diochet's algorithm. We have several theorems and algorithms that are responsible for this optimization and you know um, optimization and factorization problems, right? So you are seeing that a lot. So what we are going to do is we are going to start talking about uh, quantum computers now. So what's popular these days is this particle fever, right? If you have not seen this documentary, you should watch it on YouTube or Netflix. It's quite popular out there, and a lot of people are interested in knowing more about it. This is a video on quantum computers. So people who are new to this is a very good video that I would want to go through. Maybe I may not go through the whole video, but part of it. So let's watch this video. It gives a very good understanding of what is quantum computer, okay? So just want to make sure we have volume. Okay.
For most of our history, human technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers, basically a switch that can either block or open the way for information coming through. This information is made up of bits, which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates, which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress. To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those, it can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms need only the square root of that time, which for large databases is a huge difference. The most famous use of quantum computers is ruining IT security. Right now, your browsing, email, and banking data is being kept secure by an encryption system in which you give everyone a public key to encode messages only you can decode. The problem is that this public key can actually be used to calculate your secret private key. Luckily, doing the necessary math on any normal computer would literally take years of trial and error. But a quantum computer with exponential speedup could do it in a breeze. Another really exciting new use is simulations. Simulations of the quantum world are very intense on resources, and even for bigger structures, such as molecules, they often lack accuracy. So why not simulate quantum physics with actual quantum physics? Quantum simulations could provide new insights on proteins that might revolutionize medicine. Right now, we don't know if quantum computers will be just a very specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there's only one way to find out. This video is supported by the
All right, so this was the video on quantum computers that I wanted to show you. So let's get into the details of quantum computer, and in general, why we are here, and the curiosity you might have about it. Let's solve it, okay? So these are some of the semiconductor electronics innovation, or innovation in general. Mankind's greatest innovation has been from printing press to steam engine, and semiconductor electronics comes at number 4. So where would the quantum computer sit in here, right? That is the question. So this is the first semiconductor, first integrated circuit in 1958 was devised. And this is a quantum supremacy achieved by Google in 2019, okay? So brute force interconnects work for a few devices, but not millions of devices, okay? So that's the question we have to answer. The demand for quantum computing is very high. Time magazine says that quantum computing will change everything. Travel, logistics, chemistry, pharmacology, climate modeling, financial analysis, cryptography, and so on. Okay, so why we are here again is the thing that differentiates scientists is purely an artistic ability to discern what is a good idea, what is a beautiful idea, what is worth spending time on, and most importantly, what is a problem that is sufficiently interesting yet sufficiently difficult that it hasn't yet been solved. But the time for solving it has come now. Okay, so that's why we are here. The time to solve has come now. Okay, so this is the bits versus qubits, right? So let's go through the fundamentals of a quantum computer and what it is all about, right? So as you see, 1 or 0, is it a false or a true, depending on the charge. Versus in the case of quantum computer, we look at a block sphere like this. And block sphere can have multiple states, 2 to the power n paths. You see, a phase of a quantum computer can have any of these numbers and everything in between. You see, this is a qubit, right? There's a 2 to the power n paths. So a qubit is 1 or 0 at the same time at different proportion, okay? And right now, the question is error correction, how you are able to do error correction, and how are you able to get high quality qubits to be able to have reproducible, repetitive results. Okay, so that's your superposition, and this is a superposition state where when you pass the uh, qubit through the Hadamard gate, you get into superposition. Okay, so we'll talk about that in a moment. So currently the quantum computer that is quite prevalent at IBM or at Google or at Rigetti, right, out of Great Britain, is based on quantum annealer. Okay, quantum annealer, or an inductor is there, Josephson junction in between the two capacitors, and coupling to quantum bus, and in and out coupling readout resonator. And this particular circuit is put in the coldest place on the universe, right? It's like almost negative 273, absolute zero temperature, right? It's the coldest place on Earth, so that the superconducting properties can be realized. And at this moment, and then when you pass your microwaves through this circuit, you are able to get quantum experience and results. All the properties of quantum computer, like entanglement and superposition and all the other properties that the video explained, you are able to experience it. But there is always a problem of noise. There are a lot of noise in there, and this noise needs to be corrected. We call it error correction, and there are quite a lot of ways you can correct errors. Okay, so we go into detail in the two-day class. So there are 5 different technologies that is being tried right now, right? So there's superconducting loops, current, inductor, capacitor, microwaves. You have this particular setup at Google, IBM, Rigetti, D-Wave. They use this quantum annealer. A resistance-free current oscillates back and forth around a circuit loop. An injected microwave signals excites the current into superposition state, right? So let's see how long this quantum computer is active. The longevity is 10 to the power 5, negative 5. The 10 to the power negative 5. 0.05 multiplied by 10 to the power negative 5.0005 seconds, and logic success rate is 99.4%. Then there is Honeywell and IonQ. They have trapped ion-based laser-based, electrically charged atoms or ions have quantum energies that depend on location of electrons. Tuned laser cool and trap the ions and put them in superposition state. Okay, so that's the greater than 1,000 seconds, 99.9% logic success rate, right? And then Intel and HRL is doing silicon quantum dots. These, this particular one, these artificial atoms are made by adding an electron to a small piece of pure silicon. Microwaves control the electron's quantum state. Okay, this is Intel and HRL is doing this. Then Microsoft has this topological qubit, which is a very, very high quality qubits, right? Quasi-particles can be seen in the behavior of electron channel through semiconductor structures. Their braided path can encode quantum information. And then there's a lot of news about diamond vacancies based quantum computer. A nitrogen atom in a vacancy add an electron to a diamond lattice. Its quantum spin state, along with those of nearby carbon nuclei, can be controlled with light. So that's the diamond vacancies based quantum computer. So all of these have seen promises out there, and a lot of investment is being made in this area right now. And we will see in future what we can get, okay? But the most promising technology is the superconducting loops, followed by the trapped ion. These are the two current generation of quantum computers that are available on the cloud today, okay? So there's, in the cloud, you see a lot of these different quantum computers available for your access. You can send instructions and get response. And we'll see a demo of that later on, okay? These are the computers who are, these are the companies who are pioneers in quantum computer: IBM, Google, Alibaba, Microsoft, Intel, Honeywell, OneQubit, CQC, D-Wave Systems, IonQ, QCVED, QSimulate, Quantum Circuits, Rocco, Rigetti, Xanadu, and Zapata. And all of these have their own platforms. Some of them have built their own environment, their programming environment packages that you can run, and they have simulators that you can run quantum computer calculations, prove all the theorem that I'm going to explain you in a little bit, okay? John Preskill said that in the era of quantum supremacy, we'll be able to perform tasks with control quantum systems going beyond what can be achieved with ordinary digital computers. Google used the Sycamore quantum processor. Now, Sycamore quantum processor got inducted into Diochet Museum last week. The Diochet Museum contains artifacts and items from all the top European scientists of our times. And the Google Sycamore processor got inducted in there. Google uses Sycamore quantum processor to sample the output of a pseudo-random quantum circuit. It took about 200 seconds to sample one instance 1,000,000 times, okay? And we'll see a video of that. A classical supercomputer would have taken 10,000 years to do that, okay? Microsoft is getting into topological qubit, but before that, Microsoft Azure have given access to these 4 industry-leading partnerships to employ quantum computer on their Azure cloud. So they have OneQubit, you have Honeywell, IonQ, and QCI. These quantum computers hardware you can access via Microsoft Azure. This is the Azure stack for quantum computer. You have your applications and areas: optimization, machine learning, quantum simulation. Software tools are Q# and Quantum Developer Kit, Microsoft Quantum Solutions, OneQubit, simulators, and resource estimators. Classical hardware, you have Azure Cloud Hybrid, seamlessly trust your cloud, build on your terms. And quantum hardware like topological Qubits is for Microsoft, ion traps is IonQ and Honeywell, and superconducting is Azure Quantum. Okay, and then Honeywell, world's fastest quantum computer and highest performing quantum computer is from Honeywell today. Um, so the problem we are looking at is that we can solve, right? With standard computers, you can solve easy problems. You can use Excel, Microsoft Excel solver, and solve some basic problems, right? Using easy problems. But then you can have quantum easy problems like factorization, right? Um, or you have hardest problems, NP complete problems, like knapsack problems, or NP complete problems like traveling salesman problem, optimization problems, and other problems that cannot be solved with common computers or even quantum easy. And there are promises that these long tail problems can be solved with quantum computers, right? So what we are looking at from the quantum timeline, 0 to 5 years, we are going to see breakthrough in communication, and you're seeing a lot of breakthrough in communication right now with respect to core technology of quantum repeaters for teleporting, secure point-to-point quantum links like quantum internet, right? 5 to 10 years, like then you're going to see simulators, simulator of motion of electrons in material, new algorithms for quantum simulator and networks. As quantum computer becomes more and more available and there's more and more access available to scientists, you're going to see more and more simulators and algorithms. You're looking at sensors, quantum sensors for niche application, including gravity and magnetic sensors for healthcare, geosurvey and security. More precise atomic clocks for synchronization of future smart networks, including energy grids. Computers like operation of logical qubit protected by error correction or topologically. That's a quantum computer itself, like something that will sit under your desk. New algorithm for quantum computers, small quantum processor executing technologically irrelevant algorithms. That's 2035. In 5 to 10 years, you're going to see quantum network between distant cities, quantum internet in 5 to 10 years, so 2015. Developing and design of new complex materials, quantum sensors for large volume applications, including automotive and construction, solving chemistry and material science problems with special purpose quantum. So bit can have one or two states, qubit has many more possible states at the same time. And this is how they are explained, the alpha and beta. Superposition and entanglement. Superposition is qubit can be more than one state at the same time, right? And you have the entanglement. Qubits can affect each other over huge distances, a type of correlation equivalent to parallel computing, okay? Qubit seems to contain an infinite amount of information. The information can be extracted by measurement. When measured, qubit collapses, resulting in ket0 or ket1 with probability of alpha or beta associated with qubit's altitude, right? So you can have a qubit particle at 0 or 1, and you part it through the quantum computing platform, and you get the probabilities, alpha to tau. Okay, so this is something, so this is the ambitious claim here that the classic computer, you're going to see the bits, number of bits, and the time to factor the number of bits, right? So you have, right, like you have currently like around 100 bits, takes a second, then you have 1,000 bits takes a billion years, okay? And in 30 years, the way computer is developing and the Moore's law, you're gonna see up to 1,000 bits for a billion years. Right now, it's like more than that, okay? more than 1 billion years. But in 30 years, maybe 1,000 bits, you can do it in 1 billion years. But with quantum computer, you can do 100,000 bits in less than 100 seconds. So that is the promise, factorization promise. This is the history of quantum computer. We have to give credit to the scientists who have contributed to quantum computers. So it started with Max Planck in 1900. Max Planck, originator of quantum theory and energy quantization. 1905, Albert Einstein, photoelectric effect. 1913, Niels Bohr on atomic model. 1924, Louis de Broglie on wave-particle duality. You have object cannot be presented as only wave or particle. 1926 is Erwin Schrödinger, wave mechanics, probability for possible results measured on system. Okay. Werner Heisenberg said uncertainty principles, right? Some probabilities of quantum object cannot be known exactly at the same time. Erwin Schrödinger said thought experiment is Schrödinger's cat, quantum superposition. He explained that quantum object can be in more than one state at the same time. And then Einstein, Podolsky, and Rosen came out 1935 thought experiment called EPR paradox. Interaction of particles, quantum object can affect each other over a long distance. They call it spooky distance, spooky action at a distance. Okay. Both their position and their momentum can be measured more accurately than uncertainty principle allows, unless measuring on one particle instantaneously affects the other to prevent this accuracy, meaning that information is transmitted faster than light, which opposes the theory of relativity. Spooky action at a distance, entanglement. Okay. Then Charles Bennett and Stefan Weisner, first use of phrase quantum information theory, first suggestion using entanglement as a communication, okay, for giving rise to a quantum internet. And this was a 1981 MIT Endicott House Physics of Computation conference, where all of these luminaries joined to talk about quantum computers. In 1980, Yuri Ivanovich Manin proposed the idea of quantum computer in 1980 in his book Computable and Uncomputable. Richard Feynman, nature isn't classical, damn it. If you want to make a simulation of nature, you'd better make it quantum mechanical. By golly, it's a wonderful problem because it doesn't look so easy, okay? I worked in Dr. Feynman's lab at Cornell University in 2001 to 2003 in their cyclotron lab in Cornell University. Okay. Quantum computing history, Charles Bennett and Gilles Bessard, right, proposed cryptography based on quantum computer, quantum mechanics. Universal quantum computer, quantum theory, a Church-Turing problem, the universal quantum computer. Okay. Then Charles Bennett and his team demonstrated quantum information can be transmitted under the principle of entanglement. Right? Key knowledge is starting point of many quantum algorithms and quantum error correction. Peter Shor, I have a video on Peter Shor, showed the possibility of factoring a number into its primitives on a quantum computer. And Peter Shor, when he showed that you can factor a number using quantum computer, that's when the industry started paying attention to quantum computers, because they said, hey, quantum computer can factorize a problem easily, and that was an interesting demonstration that he showed. And that showed that you can break encryption, you can break a lot of things, you can factorize large numbers. 128-bit encryption is a danger that is running all of your internet, all of your banking, credit system, all of the safes, and all the secrets. Okay. Love Grover, 1996, created ultra-fast Grover's database search algorithm for non-indexed database can be used to crack codes. Okay, this is the Grover's algorithm. Then David DiVincenzo created DiVincenzo criteria for implementation of quantum computer. A scalable physical system with well-characterized qubit, the ability to initialize the state of qubits to a simple fiducial state. Long relevant decoherence times, a universal set of quantum gates, a qubit-specific measurement. In 2004, Robert Solf and Michael Deverett invented circuit quantum electrodynamics, laying foundation of coupling and superconducting qubits. 2007, Robert Slopfer and his team invented Transmon superconducting circuit, reducing sensitivity to the charge noise. IBM also adopted this concept, and Google later on used this concept. 2010, D-Wave System released commercial quantum computer annealer. IBM made quantum computer available on the cloud. This is the integrated cryogenic qubit control. So you have your 20 millikelvin temperature at qubit board package. It starts with control electronics. You have a refrigerator, requires several attenuators, filters on each line, and this is how the temperature changes. It starts at 300 Kelvin, going to 4000 Kelvin, control chip board and package, and then 20 millikelvin, which is the coldest temperature in the universe. So this is a video, this is a noise, how the quantum computer sounds. This is the sound of quantum computer. This is how the quantum computer sounds.
To sounds of IBM.
And you are able to access this computer from, I'll show you how to do that, and submit a circuit to this computer that is sitting in Yorktown Heights in upstate New York. Okay, that's the IBM quantum computer. We're going to go back to our slides. So we were here, we were looking at the sound. So Professor Dario Gill, he's the director of IBM research in IBM in Yorktown Heights, New York. And this is a very interesting video where he explains the origin and how the quantum computer can be used in application today. Okay, so we are going to just go over that.
Hello, I'm Dario Gill, and I'm speaking with you.
I'm just going to start full screen.
Hello, I'm Dario Gill, and I'm speaking with you from the Yorktown Heights Research Laboratory. It serves as the headquarters of IBM Research, and today it's a great pleasure for me to share with you a perspective of the quantum computing era that is emerging and the implications that it will have for science, for discovery, and for business at large. It is clear that the world is being challenged with ever more complex problems to solve. The coronavirus and COVID-19 is a powerful example of the challenges we confront in humanity as we try to understand some of the deep functioning of nature and the implications it has for all of us in our societies. Here, in the context of dealing with a structure that is no more than 100 nanometers inside, we're struggling to figure out ways how to deactivate the functioning of the virus. Now, we know that computation can help us. If we look at the inner structure of the virus, we see these spiking proteins. And these proteins can be modeled and understood. And therefore, we could use them to then explore different kinds of compounds that could deactivate how they function. Here, supercomputers can come to help us. We can use these most powerful computers to model this protein structure. And we can use another powerful force, which is the powerful force of joining the resources and the capability across institutions. In moments of crisis, it is particularly important that we all come together. And that's why we were very proud to coalesce and create in partnership with the federal government and other institutions in the tech sector, as well as academia, the COVID-19 High Performance Computing Consortium, where 30+ members have aggregated over 400 petaflops of computing power and over 100,000 nodes to go and pursue a broad portfolio of projects that can help us understand the pandemic, understand the evolution of the virus, and accelerate the pace at which we can develop antivirals and ultimately vaccines. What this tells us is that when confronting with exponential problems, we have enormous computational demands. In fact, exponential problems require exponential computation. And today, we're fighting the pandemic within the context of the computational paradigm we have, the world of bits. But there's another computational paradigm that is emerging, and is the world of qubits. So moving forward, bits and qubits will be foundational computational paradigms with which we can tackle complex problems in the world. So let's try to understand the difference between them and where the power of qubits rise. If we look at the left-hand side, it's a way to describe, and we're going to use these diagrams throughout the presentation to unpack the power. We're seeing a circle and two dots. When the dot is in the north pole, that's a 0. When it's in the south pole, it's a 1. That's a classical bit to state. Now, a qubit is the unit of information in quantum world. And here we get to have, let's depict it as a sphere, a 0 and a 1. And we can have them in this superposition state. But we have a special trick that is available to us. Not only we can have them positioned in this sphere, but imagine that each one of these now is like a little moon that is in this sphere, and we can rotate the moon. So here you're seeing that the bottom sphere has been rotated slightly, so that's why you see a little bit of blue and pink. And we could rotate it all the way. So here's a 180-degree shift. So we have this notion of phase. Quantum affords us 3 superpowers that are exhibited in the qubits. They are the powers of superposition, the power of interference, and the power of entanglement. So let's unpack those. The principle of superposition is actually quite straightforward to understand. So let's start on the left-hand side. We have our North Pole 0 or South Pole 1. And if we add those two states, now we have a superposition qubit that has both a 0 and a 1 simultaneously, North and South Pole. Now the right diagram is the same, but now we're going to do a little trick. We're going to apply a gate, a quantum gate. And what we did here is, remember, we get to change now, we get to rotate these little moons, right? So we rotated it 180 degrees, and now we have a 1. So now when we do the addition of 0 plus 1, we end up with a superposition state, but notice that it's different than the one on the left. We have still a 0 and a 1, but now with a rotated state for the 1. Now, that is going to be very powerful to then leverage a second really interesting thing, which is the principle of interference. And this is not an operation that we get to perform in classical bit world. So here in this example, we have a 0 and a 1 on the left, plus this new state that we created, which is also a 0 and a 1, but with this rotated moon. When we do this now, we get to interfere those two states. And notice something really interesting happens. We've canceled the 1 state, and we've ended up with that 0 state. We've done that because we've interfered the states. So the next opportunity that we have right now is how many states can we create? And the beautiful thing in quantum is we get to create an exponential number of states. So let's look at a system that has 5 qubits in this case, we're depicting these qubits as independent qubits, right? You're seeing them on the left, zeros and ones, and they're getting multiplied. We have 5 of them. So the number of states that we can create now in our quantum computer, depicted on the sphere on the right, it's 2 to the power of the number of qubits we have. In this case, we have 5, so 2 to the power of 5 is 32 states. So we're seeing 32 of those little moons. Notice that in this case, we did not incorporate any phase. They're all pink. The powerful aspect of using this property called entanglement in the quantum world is that we can create now states like the one depicted on the right, where we have these combinations of pink and blue, where that end state cannot be described as the independent product of these 5 qubits in this case, since we have 32 states. What this tells us is actually something very profound. And that is that you could have an end state in your quantum system that you're using to process information that cannot be described as the independent components of the qubits that make the whole state. There's a lot in there. It's a very profound statement, and it is the basis of the power and the complexity of quantum machines. So let's bring that all together to give you an intuition for how an algorithm works in a quantum computer. What we do is that at the beginning, let's say in this case, we have a 5-qubit quantum computer, is that we prepare the computer to be in a superposition of states. 2 to the power of 5, 32, you have those 32 dots that you see on the left in pink. Then we have to encode the problem. We have to inject data into the quantum machine. The way that happens is that that encoding gets done through entanglement. So notice that what we've done now is that some of those states are now changed in phase. You're seeing those depicted as blue and some are pink. Now in our machines, not only we have this superposition, we have exploited the property of entanglement to do the encoding of information. And the principle of interference comes from the fact that we can now take these states and combine them and interfere them with one another in such a way that we get to cancel things out and maximize the right answer. So many things fall away and the right answer gets maximized. We perform a measurement and we get a result. Notice how very different that is from classical bit-based operations. And there is a really important relationship between this entangled property and the amount of information that we can process. And this relationship is exponential. What this table shows is the number of classical bits, zeros and ones, that are required to represent that complex entangled state that I just described. And here's an amazing number. By the time you have 100 perfect qubits that are entangled with one another, if you needed to describe them using zeros and ones, you would need to devote every atom of planet Earth to store those zeros and ones. Clearly, that's not possible. In fact, by the time you have 280 qubits, you would need every atom of the known universe. So that it tells you that there's this exponential relationship between this special property of entanglement and the representation of information. Why does this matter? Well, it matters because it turns out that despite how powerful our classical computers are, the reality is that there's a vast set of problems in the world that they cannot tackle. From an information theory perspective, we would say that really classical computers can tackle easy problems, things that don't have an exponential number of variables in them. Remember, in the case of the virus, as an example, that modeling nature is an example of an exponential problem. But so are other problems like factoring and problems in optimization. In fact, there's a vast number of problems in the world of mathematics that have that character, and those problems are deeply important for business the world over, for optimization and the future and machine learning and developing new molecules and chemistry and the life sciences and beyond. Now, The reality of it is that you say, well, that's very interesting and the theoretical underpinning, but can you actually build these machines and access these machines? And we also recognize that for most of history, to access computing power, you had to build it and maintain it yourself. But now we're in a situation where even these very special machines, quantum computers, can be accessed by anyone in the world. In fact, the system looks as follows. You can sit in front of your terminal, write your program. You can send your zeros and ones. And when they get here to the laboratory where we are as an example, we convert those zeros and ones to microwave pulses. They operate about 5 gigahertz. And we send them down a cryostat that operates about 15 millikelvin temperature. And we get to use those microwave pulses to manipulate these qubits, to perform those superposition and entanglement and interference operations, and then return the result to the user who is using a regular classical computer. This is what the inside of these beautiful machines look like. I say beautiful because they're really gorgeous pieces of engineering and science. And you're seeing the inside of this cryostat, that golden chandelier. And those wires are the means by which we send those microwave pulses down. At the very bottom of that golden chandelier is where we have the quantum processor itself, where we perform those operations. So if we go and look inside, this is what a quantum processor looks like. In our case, in IBM, we use superconducting technology. Specifically, we use a qubit device called the transmon qubit. And what you're seeing is, at the core of it, if you look at the bottom right-hand side, we have a device which is called a Joseph junction that is about 100 nanometers by 100 nanometers, roughly the size of the coronavirus, in fact. So 100 nanometers by 100 nanometers, and essentially allows us to create an artificial atom with a ground state and an excited state that is the basis then with which we can couple it to other qubits. And you're seeing on the right-hand side those wiggly lines that we've labeled microwave resonators. And that's what allows us to couple the qubits with one another and then perform these entanglement and interference operations that give quantum computing its power. We build these quantum chips here in the laboratory from which I'm talking to you today in Yorktown Heights. Now, with those units of information, the very important thing that is being created is a rich and vibrant world of quantum circuits. This is what's really next in the world of quantum. So let's explore them a little bit. A quantum circuit is going to be the unit of value for your business. The qubit is the unit of information, but a circuit is the unit of computation. So let's try to understand what is a quantum circuit, and let's look at its anatomy. This is what a quantum circuit looks like. So let's decompose this into pieces. The qubits are depicted by these horizontal lines. In this case, we're depicting a circuit that has 4 qubits that you see here shown. Now, the gates are how we control the qubits, and you read the gates from left to right. So it's the sequence of placing these gates that is the basis of creating a circuit. To construct these circuits, we have many quantum gates available to control these circuits. So this is analogous to the way we do controls in the world of bits. So in the world of bits, we're all accustomed to that, behind the scenes, we have these ands and ors and nots, etc. So similarly, in the world of qubits, we have a different set of operations. Remember, some of those operations are the very idea of doing the rotation to one of our little moons that I was depicting before, right? Introducing a phase change. And I showed before a Z operation that performed that rotation that allows us to do that interference operation. So let's do a comparison between a classical circuit and a quantum circuit. Here in a classical circuit, what you witness here is that you don't get to see blue moons, right? There's no rotations. Everything here is pink. And that you got these single states that in this case we're seeing moving the sphere. But notice what a contrast is going to look like when we actually implement a quantum circuit. So let's look at what a quantum circuit looks like. So in this case, we're implementing Grover's algorithm, which is a basis for performing search operations. First of all, you notice the complexity has increased greatly, right? We have these superposition states. Now you're seeing that we get to perform these operations where we do rotations. So here you're seeing blue. We're performing operations of interference. You're seeing some of those little moons getting bigger and bigger in size. That is telling us we're converging to some important answer, and that is how we get finally to the answer. So if we put them side by side, just visually, you can get a sense that a classical circuit can never exploit the vast computational space that a quantum circuit can. It's the visualizations give you this intuition of the richness with which we can access this large state. And the beautiful part of this is that we can have many classes of circuits to do different functions. So for example, this is a circuit that is designed to model financial risk. Here's an example of a circuit for the world of chemistry, right? To measure the energy of lithium hydride that is important for the development of new battery technology. Here's a circuit that is a unique form of a classifier, a new approach to machine learning applications. So what we're very excited to share with all of you is the fact that libraries of these circuits are emerging, and that there's going to be this richness of circuits that allow you to perform different applications that we are going to be able to embed in the programs that we all use and create to create business value. Libraries of circuits that get embedded in classical programs that now combine the best of classical programming and the best of quantum power. It is important to realize that not all circuits have equal value, and that there will be circuits that you can implement classically far, far better. Because if you're not exploiting that computational space, if you're not exploiting these ideas of superposition and interference and entanglement in the proper way, you don't get there. Now, we're very fortunate that some of the best minds in the world are thinking really hard about
So
this
you kind of
problem.
get an idea about this. You can watch this later on. I'll put the link later on in the chat. So what we are looking at here is the quantum computer, and Dario Gil explained this quantum computer to us.
Hello, I'm Dario.
In detail. So this is the D-Wave systems. We are going to go through this video very quickly. D-Wave system is another quantum computer that is out there, quite popular since 2010, and they specialize in optimization problems and scheduling problems. So we'll go through that briefly.
We are coming to you live from is a stone's throw from our warehouse. And what would you say if I told you that they invited us in for a behind-the-scenes dual curved tempered glass side panel? Check it out now at the link below. So in 2007, D-Wave introduced their first quantum processor. Now, with only 16 qubits, it wasn't especially powerful, but the point wasn't whether you could or couldn't solve the same problems with a pencil and a piece of paper. The point was that this scalable approach would allow them to ship the world's first commercial quantum computer, the D-Wave 1, in 2011 with 128 qubits, followed by 512, 1,000, and 2,000 qubit designs in 2013, 2015, and 2017, respectively. And adding more qubits is the key to increasing performance, because the more qubits you add, the more complex the problems that you can tackle. You see, quantum computing doesn't work like classical computing with ones and zeros, where you feed it a question and then it spits out an answer. Instead, a quantum processor takes all of the parameters you feed it and works on every solution, pointing you at one or two or maybe even more optimal solutions. So they're not perfect for everything. I don't think there's a single person in this building who expects Call of Duty Black Ops 10 to run on a D-Wave Mach 5 quantum gaming rig or anything like that. But for scheduling out a sports team's games over the course of a season, for tackling problems like logistics, climate change, and energy distribution, or for conducting AI research, these puppies right here have the potential to completely disrupt the existing players. So then let's go have a look at one, shall we? Now, there are only a handful of customers in the world who have actually ponied up the price of a D-Wave system, including high rollers like Lockheed Martin, Los Alamos National Lab, Google, and NASA. But D-Wave themselves have a handful of their latest generation 2000Q systems running here at their headquarters that are available through the cloud. Just make sure that you don't turn off any of the ones with a delightfully low-tech online sign zip tied to it. It might be doing very, very important research. So from the outside, a 2000Q doesn't look that different from any other compute cluster with a few black racks. And when you open up door number 1, there's not much at first glance to indicate that there's anything special about it. You'll find a network switch, a UPS for battery backup, a normal server responsible for monitoring some monitoring devices that, wait a minute, 7, 8 degrees milli-Kelvin? We're gonna have to get back to that later. There's also a second server that takes a problem and translates it into machine code using custom room temperature electronics to generate high precision analog signals that it then sends to, as we promised, just about the coldest place in the known universe. The single, yes, just one chip, single codename Washington quantum processor at the heart of this machine. But where exactly is it? It's not behind door 2 or door number 3. Back there, you'll find the first and second stage pumps that are used to create a vacuum around the processor to thermally insulate it and its cooling system from the outside world, as well as a compressor for the aforementioned cooling system. And you also won't find it in this barrel-shaped doodad. That is actually a liquid nitrogen filter that removes impurities from the coolant mixture of helium-3 and helium-4 isotopes, and is one of the things that allows D-Wave systems to run for years at a time. A critical feature, given that the chip kind of locks into a certain configuration once it's supercooled. And if you heat one of these puppies up back to room temperature, it can take up to 2 days to cool it back down and up to 4 weeks to finish the rebalancing or recalibration process. No, to find the actual processor, we have to go past this first door on the left here that handles connecting the all business racks at the front to the giant box here that was hiding in plain sight that I'll be referring to as the party in the back, or per D-Wave's gentle suggestion, the shielded enclosure. This right here is effectively a big Faraday cage and the first of 16 layers of shielding that are designed to shield the power lines and preserve the integrity of the signals to and from the quantum processor to the greatest degree possible. And that was a very intentional pun, by the way. Now, normally these rooms are closed and there is a series of casings on top of this apparatus here to maintain the vacuum around what is effectively the motherboard of our quantum computer. But they had one open for maintenance today, so we got to get up close and personal. The thing is peppered with probes and sensors, heat exchangers, data wires, but the 5 big plates are really the main attraction here. Each of them represents a different stage of the cooling system. The top one gets signals from the outside world on copper wires and runs at a frosty 70 degrees Kelvin. The next one down uses the same fridge and these braided copper conductors to get down to 4 degrees Kelvin, which is both low enough to condense helium to a liquid and to switch over from copper wires to the superconductor niobium. The middle plate here uses vacuum helium-4 to drop our signal wires to 1 degree Kelvin. The fourth uses helium-3 to get us to about 1/10 of that. And the final stage uses a sophisticated mixture of those two isotopes to drive this entire filtering and shielding apparatus, as well as the processor inside, down to its typical operating temperature of about 0.015 degrees Kelvin, damn near absolute zero. But why does it need to be so cold? Niobium already superconducts at 9 degrees Kelvin. Interstellar space is 3.1 degrees Kelvin. Our solar system is even warmer. We're talking 0.015 degrees Kelvin. Well, this superconducting chip here is what's inside there. And it's connected via 400 superconducting wires. And this is kind of like the pins on a CPU socket. And what it's doing is it's using quantum mechanical effects to process information. So for that to work, these effects need to be significant enough to use them for computation, which means that the temperature needs to be well below the energy scale of those quantum effects. If it wasn't, then the data you'd get would be very, very noisy, corrupted by heat-related quantum effects. That's why the colder they can get, pretty much the better. And getting even colder in the future may actually be practical. So this generation of D-Waves processors consumes no power and outputs no heat, meaning that the 20 kilowatts of power that are required to run the system is just dedicated to the cooling system. So unless they wanted to go colder, this energy cost doesn't change whether you're running 100 qubits or 2,000 qubits. That's just the sweet spot of practicality and functionality today. And more cooling is far from the only thing on the horizon. The future's looking bright for our neighbors here at D-Wave. They don't have a 50-year vision yet necessarily, but in the nearer term, they don't really perceive anyone else in the space as a real competitor with a commercializable technology. And with more R&D focus, they think their system could be as compact as 3 or 4 racks and capable of taking on some of the hardest neural network problems that we face in the years to come. And you know what? Sounds pretty good to me.
So this
Dollar
was
Shave Club
the
is kind of amazing. You can get the
this was the D-Wave system. Okay, so we looked at the IBM's computer. We looked at the D-Wave. So let's look at the D-Wave computer. And go through the details of D-Wave Leap. We'll go and log into D-Wave Leap and try some problems, okay? So we're gonna go to D-Wave Leap. This is the D-Wave Leap. You can log in to D-Wave Leap. And once you log in, okay, let's see. Probably send me the code here. There we go. Let's see if I got the pause this and check the email. Okay, I got the code. All right. Okay, so we have we put the code here and we submit, And once we submit, we are in. Okay. So this is expired now. I have to log in with a different because I have used it up. So I'm going to sign up with a newer email address. Okay, so let me just try that. Okay. I'm just gonna get a new account. Okay, just bear with me. I'm going to confirm the account, and then there we go. Okay, so I was able to get the okay, trial plan use 0%, so I'm good. So this is the D-Waves quantum computer. So they have a lot of problems that they have solved here, like Sudoku, simple ocean, nurse scheduling, satellite placement, QBoost, pipelines, MeQubo, maximum card maze, immunization strategies. So all these are problems that they have already solved. Image segmentation, snapsack problem, factoring, graph coloring, map coloring, job shop scheduling, graph partitioning, crop rotation, airline hub location. All of these are different D-Waves examples that they have solved already. And we can go over it in a moment. Before that, we will just go through some interactive demos, okay? So you can start an IDE, you can set up a problem, and D-Wave will solve the problem for you, right? These are the examples. We'll go through that in a moment. First, let's run the demo first. So factoring by running multiplication circuit in reverse, okay? So integer factoring is a process of finding factors that when multiplied together give a target integer. For example, the factoring of 15 are 3 and 5. Because factoring large numbers can be extremely time consuming is the basis of the RSA encryption, the RSA method of cryptography, right? Public key cryptography system. Because factoring large numbers is very difficult. But the D-Waves quantum computer factor numbers in an entirely different way. Turning a multiplication circuit into a constraint satisfaction problem allows the quantum computer to compute inputs from fixed outputs. Essentially, this means running a multiplication circuit in reversal. Okay, so let's look at 21. 21 is 7 and 3. The number you choose will be submitted, right, for constraint satisfaction problem for a D-Wave quantum computer. So this problem will, in the background, run a real quantum computer, right? Demo uses small number for which finding factor is simple. However, same technique applies to solving complex constraint satisfaction problem. So now it's going to try and trial and error, 21 by 3, 7 and 3, and 21, 5, 21, 6, 21, 7, 3. Okay, so you got 3 and 7. For small numbers, a basic approach like trial division, in which we methodically try dividing our number by candidate factors, one after the other, is trivial as the number grows. However, the sequence of simple operations quickly becomes extremely time consuming. So factoring and encryption in 2009, 512-bit factoring was estimated to take months, 768-bit factoring over 1,000 years, and 1024-bit factoring 1 million years. And you have the classical computer factors, right? The quantum multiplication is in Boolean logic. You can reverse engineer a 3-bit multiplication circuit to find the product of two factors. While factoring can be difficult classically, it's easy to check the result is a simple multiplication circuit that we can use to see whether two factors are valid. Okay, the factors are input on the left, the binary values flow through the gates in the circuit and yielding the product on the right. By transforming this multiplication circuit into constraint satisfaction problem, we can compute a set of input values from the known output value. This is equivalent to factoring. And a multiplication circuit is an example, right? So you see the programming technique used in the demo can be applied to all Boolean logic in a broad class of constraint satisfaction problem, right? So now you're looking at classical computer, A, B, and C, and an AND gate, and quantum computer, qubit, and couplers. This is how they are represented, right? A constraint satisfaction problem can be programmed into quantum computer, one logic gate at a time. Shown here, an AND gate is a constraint between two binary inputs and one outputs. It output one only when both binary inputs are one. Binary constraints can be mapped to a set of qubits and a coupler so that those qubits associated with the constrained inputs and outputs with high probability find values consistent with constraints. For the AND gate, the qubit associated with the output seeks a value of 1 if and only if the qubits associated with the inputs are all settling into value of 1, otherwise it seeks a value of 0. A quantum computer simultaneously seeks input and output values that satisfy all constraints of a logic circuit. Creating a mapping, you have a circuit, you have a transformation to a qubit-based circuit, and this is a qubit-based circuit transformation, a 3-bit multiplication. And so in the network shown on the right, the full adder transformed to yellow pentagram and the half adder to blue squares and a gate to pink triangles. While it's possible to create wires in the quantum computer matching the interconnection in the circuit, the problem mapping is more efficient if the number and the length of wires is minimized, right? So centered interconnected inputs and outputs is reduced to single qubit rather than distributing the information across several wires. And you see that here, and now this problem is being solved in the real quantum computer. So binary values, the quantum computer returns the value of remaining variables, including the factor we seek. When we formulate a problem in this way, we are specifying the relationship among variables. So now it's going to send a job to the real quantum computer, and you'll see it solved. Okay, so now you see the real quantum computer running, and it gave you the number in 0.024 seconds. So a normal computer took several seconds. The quantum computer gave the result in 0.024 seconds. So this was the D-Waves quantum computer that ran the solution here. We have seen how quantum computer can enable a new approach to solving broad class of problems. The next one is a social network problem that you can do it yourself. You can look at the Jupyter notebook and run the next demo or run the next demo, right? So more factoring a Jupyter notebook, and this will start the D-Wave environment where you can run a Python code to run the problems. Okay, so this is the exploring Pegasus technology, topology, factoring. You can open the notebook, and then it will open the notebook for you, and you can run this notebook on a D-Wave computer on a factorization problem. Okay, so this is the factoring quantum computer. Convert to BQM, submit to quantum computer, and the summary of how it's done. Okay, so you can run the same problem of social network analysis using optimization. So it will show here how the Romeo and Juliet problem can be solved using network optimization. And then a real problem can be submitted to this is a class imbalance. And why Romeo and Juliet issue happened is because they were part of the two adversaries, and there were no connecting relationship. And when you run the imbalance, this relationship of Romeo and Juliet was the origin of instability. Previously, they were running peacefully. They were living peacefully on two sides of the river. But once this was the uh, uh, you know relationships here across these families, and then when you saw the adversaries were on the two sides of the river or the partition, when these two guys got into relationship, now we are seeing the imbalance and instability. The same thing you see in the other problems that you see in social media or in real social unrest in the case of gangs of LA or global terrorist network. So quantum computer can be used for this, right? So this was the CEI in 2012. There were groups here, groups here. There was a partition in between. Syria in 2013 was quite complicated, where there were other people got introduced in the society, and that started the instability, right? And then you run the quantum computer equilibrium, and you see that unlike 2012, it's not possible to balance the network from 2013. Shown here is a minimum structural imbalance in the network with the frustrated edges shown as dotted lines. The presence of frustrated edges is a predictive of violence. Okay, so this is where you anticipate violence in this dotted line. Okay, so basically you see this is a quantum processor to 0.497 milliseconds, 497 milliseconds, and the CPU is taking much longer. So you have just run a small example problem on QPU. Let's now take a look at different set of problems evaluating performance. Structural imbalance in the graph results from presence of frustrated loops. Recent research has demonstrated that the system of intersecting frustrated loops create conditions where quantum computers can provide advantage. Okay, so this is, you see that this one takes much longer time. The classical computer versus the quantum computer was much faster. So find a non-interacting drugs from database using maximum independence sets. Evaluate communication network redundancy by finding division with densenet set of interconnecting maximum cuts, and assign frequencies to cell towers with graph coloring. So these are the problems you can solve. We will go back to the dashboard. Let's do the nurse scheduling problem, and this will start IDE. So you see we're going to execute this in a D-Wave leap where a complex nurse scheduling problem can be solved using D-Wave's quantum computer. We'll execute the code, and you will see that in less than a second, you will see nurse scheduling problem solved. Of which nurse will be scheduled to go next, right? So this is the problem. We are going to go into the code, right, and then execute it. Okay. So now it's running the code. Binary quadratic model. It's a quadratic equation. Sending problem to hybrid sampler to the quantum computer, and you saw the problem is already solved, right? Which nurse will be scheduled in what shift, okay? So this was a very simple Python program. We submitted, and we got the result, okay? So this was an optimization problem run on a quantum computer, okay? So we'll go back to the slides now and talk about Google's quantum computer, okay?
The tantalizing promise of quantum computers is that they can do certain tasks exponentially faster than classical machines. And the quantum supremacy experiment is proof that this is indeed the case.
The word quantum computer is a little bit misleading because it sounds like a computer. And when people think of computer, they think of a phone or a laptop. The truth is the phone and the laptop and even a very powerful supercomputer all operate according to the same fundamental rules. And a quantum computer is fundamentally different.
The classical bit stores information as a 0 or 1, and a quantum bit can be both 0 and 1 at the same time. If you have 2 quantum bits, then there are 4 possible states that you can put in superposition. With 3 qubits, it's 8, 4 qubits, it's 16, but grows exponentially.
The nice thing about quantum supremacy is that this is a very well-defined engineering milestone.
In a nutshell, what we're trying to do is we're trying to show that experimental quantum computers can surpass the best supercomputers in the world.
To actually demonstrate quantum supremacy, we have these 3 steps. First, pick a circuit. Second, run it on the quantum computer. Third, simulate what the quantum computer is doing on a classical computer. We gradually increase the complexity of that circuit. At some point, it becomes completely impossible for the classical computer to keep up. Then we say we've achieved quantum supremacy.
We started building together the quantum chips to do this experiment. And then the evolution of the devices with more and more qubits and more complexity is very much an iterative process.
A lot of the work that we put in was not just these chips, but is also the infrastructure that you need to drive those chips. The cryostats that we install them in, all of the control electronics, software, all of this stuff is needed, and it all has to be developed.
When the experiment started, we were getting data from the experimentalists. We saw initially a beautiful straight line corresponding to our predictions.
Then right before we hit supremacy, it dropped much faster and it fell below the threshold where it needed to be.
And there's nothing we can do because we don't know how to analyze past that. So everyone's like, oh, we're screwed because it's getting really, really bad at large number of qubits.
It's like, well, maybe there's some really complex interaction between all the qubits.
It turned out that the reason was rather benign. We calibrated it a little bit better and then this problem disappeared.
So there wasn't like oh, we did it.
I think we crossed it, and then it wasn't clear that we crossed it, so we crossed it a little bit further.
It took me like a day to realize, like, hold on, this is actually experimental data. It's kind of amazing to see, how well the theory works.
The processor that achieved quantum supremacy is called the Sycamore processor.
And it's parallel processing 2 to the 53 states, which is 10 million billion. And thus that enormous amount of parallel processing is what gives it the power.
When we run a small chunks of the computation, it's the largest supercomputer in the world. Our estimate is that it will take thousands of years to complete the full computation.
Technologies are born this way. Let's say the space age started with a satellite orbiting Earth, and it was not doing much, it was just beeping.
The big technical achievement of quantum supremacy was really dependent on all this young talent who's kind of taken this and gotten it to work at a very technologically capable level.
We have reached a new computational capability. There are certain computations, the only place in the world where you can compute those things is here in our data center at Google Santa Barbara.
For the first time, we're showing that we can solve a problem that was just infeasible to do on the biggest computers ever made by civilization.
And what's exciting is now we're ready to turn this over to the world and say, let's figure out what we can do with this.
The thing that excites me most is building a useful quantum computer. When we can give a researcher a tool that is unlike any other and say, great, figure out something cool to do with it. Mankind is pretty good at that.
Okay, so this was the Google's quantum computer. We'll go through many examples of this. There's one more video. I'm not going to go through it today. But in general, this is the video of entanglement, explains entanglement. It's quite a long video, and it's better for you to go through it yourself, okay? But it explains in detail how a quantum computer gates work and how do you create entanglement and how it makes sense that entanglement can create teleportation. It gives you that, right? There's a lot of activity going on in teleportation. Researchers in China have teleported photons from ground to the satellite orbit, more than 500 kilometers above. Toshiba announced its breakthrough in long-distance quantum communication, teleporting towards quantum internet. So there's a lot of development going on in this area. This is like a teleportation circuit, optical circuit. This is a processor that's used And this is an example of how teleportation works. And this is the video from Keio University that you might be interested in.
Recently, we talked about using single photons as qubits. We're back here again in the laboratory of Professor Akira Furusawa. Professor Furusawa, thank you for being with us. And now we're going to talk about the hardware of optical quantum computers, how you can actually operate on those qubits. Here we have one of Professor Furusawa's experiments. Can you explain this to us?
Yeah. So first of all, we create time-being qubit here.
Okay.
And we make a teleportation over there.
Okay.
And teleportation can be regarded as identity operation or linear transformation.
Okay, a linear transformation, that's like addition or subtraction, is that right? Okay. So I see lots of lenses and mirrors and the like here on the table. What are they used for?
If we don't use these mirrors and beam splitters, light beam is just go straight.
Okay.
So to build a circuit, we need many mirrors and beam splitters. That is the reason why we use many optics here.
I see. So you mentioned teleportation. Over here at this end of the table, there's an experiment where the qubit is teleported from one end of the table to the other end of the table, right? So that's what you're calling the identity operation, correct? And it can be used to move data from one place inside of a quantum computer to another place inside of a quantum computer.
Yeah, right.
Good. Okay, so that's the linear operations on this table here. Over here on this side of the room, we have a different optical table with another experiment on it, right? Tell us about what's on this table.
Okay, here we are working on nonlinear operation and by using teleportation technology.
Okay, so on this table we have linear operations, which is like addition or subtraction. Over here we have nonlinear operations. That's like multiplication or division. So if we have both technologies, then we have all of the basic technologies we need to build a quantum computer?
Yeah.
Great. So this optical table, I see lots of lenses and mirrors and whatnot on the table. It covers several meters. Is this the future of how we build quantum computers using single photons, or is there another way to do it?
So to make a real quantum computer, we have to make these guys very small. For that purpose, we are making a chip like this. This is a waveguide chip. And in this chip, we have this type of circuit.
Okay, you said waveguide. What's a waveguide?
Waveguide is a kind of very similar to optical fiber.
So just like the optical fiber that brings the internet to my house. Okay.
Yeah. And by using that type of light waveguide, we are building a circuit.
So inside of this chip, you have those waveguides, and then you have, along with them, something that does the equivalent of what the beam splitters and other devices you have here on the table does.
Yeah.
I see. How large would a quantum computer that uses this technology be?
So even with this chip, and this is just a couple of gates.
Okay.
So to make a real quantum computer, we have to have millions of gates.
Okay, and it's several millimeters wide and a couple of centimeters long. Right? So if you need a whole lot of them.
Yeah. So to solve that problem, we are now developed the methodology of time domain multiplexing.
Time domain multiplexing.
Yeah. That is, we use this device plenty of time. So we use this one and the output coming back to here and do this again and again and again.
So the light comes into the chip, it gets processed a little bit, and then it comes out the other end, and then you circulate it back around and bring it through the same chip again. I see.
Yeah, and do it many, many, many times.
Okay. What are the challenges to building a system like that? How hard is it to build a large-scale quantum computer using this technology?
So I should say that optical technology itself is matured. So now we have to work on quantum error correction.
Quantum error correction, good.
So that is the last problem for us.
So individual photons, do you lose them? When we have light scattering around, like scattering around the laboratory here, it's going in all sorts of different directions. Is that a problem for a quantum computer?
In principle, yes, but to solve that problem, we use quantum error correction. For quantum error correction, we have redundancy of information. So if we have, if we lose some part of information, we can get it back to the original data.
Okay, so you can reconstruct the states even when you've lost some of the photons out of some large state of many photons. I see. Okay, thank you. So that tells us how we can manipulate the photonic qubits, execute gates on them with your technology. Tell me, what else do you need to build a large-scale quantum computer?
To make a real quantum computer, we need the ability of quantum error correction.
Ah, okay. So with quantum error correction, you take a large number of photons and use them to represent one logical qubit of data?
Yeah.
Okay.
And by using that logical qubits, we make quantum error correction. And to create that type of logical qubit, we are now planning to use photon number resolving, superconducting photon number resolving detector.
Okay, so that means you need a special detector that can count 1 photon, 2 photons, 3 photons. I see. What else do you need in terms of hardware to build a machine? Anything else?
I think that's it.
Great, that sounds good. Thank you. Thank you all for joining.
So this was the teleportation and the optical quantum computer, okay? So let's change gears, and I was planning to take a break, but we can just go and then leave early, okay? So so basically the part 2, we're going to talk about the random number generator and how do you break encryption, okay? So the quantum random number generator is quite interesting topic, okay? Because we all know random number generator out there. We have a lot of them out there. You know, you can just do it in Excel if you want. You know, just take a seed, decide a distribution, and then you can develop a random number generator. The kind of random number generator is used for creating the cryptographic keys. Those random number generators are created from a CPU heat, like heat generated by CPU. Sometimes some other cryptography based random numbers are generated from different operations that happen on CPU or a GPU. You see that all the time. That's used in the quantum computer in the encryption. Okay. But what we have seen over time is the quantum random number generator are real random. Okay, so true random number generators are real quantum random number generator that are generated from a quantum phenomenon, a quantum physics based random number generator, and that can be used to create a new type of encryption or even break the encryption. Okay, so before I go into more quantum computer, I mean, I wanted to share this very interesting view graph from physics, right? How electromagnetism is related with respect to east-west, north-south, electricity, radiation, magnetism, and how different type of forces like radiation is a centrifugal force versus gravitation is a centripetal force. So you have a mass, a proton, and an electron, and a neutron in the center, and the electricity goes from east to north, radiation goes from east to south, and then you have dark magnetism, photon absorption, and all of these phenomena are charge energy, charge on the north, energy on the south. So this kind of gives you a time, if you look at from photon absorption to light electricity to time to dark magnetism to mass to dark electricity and so on. So you see from 1 to 7, you are able to go and move things around. Okay, so this is a visuals to help you understand quantum computer better. Okay, so if you are into quantum physics, and if physics is your passion, then if you look at this, I sometimes look at this chart for like 15-20 minutes, and I come up with so many analogies and understanding of all the phenomena that are running around us on a regular basis. So a quantum phenomenon is very, very interesting. So like when you look at a bubble, okay, like your kids, they play with the soap bubble. So those soap bubbles are an example of a quantum phenomenon. They take the minimum space wherever they are at. So I was with my daughter at San Francisco Exploratorium last weekend, and we were playing with the bubbles. We were playing at different physics experiments there, and I could firsthand see that bubble always takes the minimum space wherever they are kept, and they keep changing space. That's the quantum phenomenon. As we talked about earlier, the bits versus qubits, and how the quantum random numbers can be generated. Okay, so you can create random numbers through three methods. You can have a simulation like Monte Carlo simulator or sampling distribution. You can do it for banking encryption, QKD, or fundamental science like loophole-free Bell test. So you can generate random numbers through this. So what is a quantum random number generator? So it seeks to be a new norm of generators of random numbers, not only in cryptography, but also in many other fields such as AI, Monte Carlo, such as simulation sampling. A quantum random number generator, apart from its technical merit, would have fascinated Einstein. He would probably be happy that theory of relativity led to the outcome. The approach also suggests something about quantum theory, a random existence of which Einstein denied when he claimed that world does not play the dice, okay, with God. Perhaps not, but mankind has figured out how to create its own superior quantum-based and completely random dice, right? So there are optical quantum random number generators like branching path generator, time of arrival generator, photon counting generator that we saw earlier in the video, attenuated pulse generator, generators based on quantum vacuum fluctuation, generators based on phase noise lasers, generators based on amplified spontaneous emission, generators based on Raman scattering, generators based on optical parametric oscillators. And you have the pseudo-random number generators through an algorithm and a seed called linear congruential pseudo-random number generator, or cryptographically secure pseudo-random number generator, or true random number generators through physical processes like chaotic random number generator or quantum random number generator. So you can have a uniform private, cryptography through this. So what are the vulnerabilities of random number generators in general? In 2012, the biggest scan of transport layer security and secure shell SSH over the internet unveiled surprisingly widespread vulnerable keys. Haninder et al. computed private keys of 0.5% of HTTPS host and 1.06% of SSH host by exploiting known weaknesses of RSA and DSA when used with insufficient randomness. This was a big deal. A weak random number generator, bad cryptography. Cryptography is only as strong as its weakest link. And that's it. You are able to get into any door you want. Okay, so this quantum random number generators are ideal intrinsic randomness, unpredictable and private, uniform, almost uniform after post-processing. So the way it works is you create quantum entropy and then measurement, you have a side information, you have randomness, extraction. Sources could be in mixed state, measurement devices and environment introduces noise. Proper modeling and characterization of quantify the minimum entropy condition on the side information. Okay, so this is the deviation from modeling, defective parts, poor choice of extractors. So these are the problems with the quantum random number generator. So, so basically you have, you can turn the adversarial tools into diagnostic tools and can be examining underlying randomness without knowing the internal working principles. So you have your introduction, method, and results. This is the quantum random number generator that are given by the QUT under test. Okay. So this particular random number generator is homodyne measurement of vacuum state, ADC dynamical range optimized for maximum secure entropy, secure against classical side information, real-time secure bit generation rate of greater than 3.5 gigabits per second. And you are able to create random numbers. You see here, you have the random number generators. This is an online server that can generate random number generators. So we're going to open this, and you're going to see this is a website of ANU, Australian Neuroscience Quantum Random Number Generators. And this is their setup. This website offers true random numbers to anyone on the internet. The random numbers are generated in real time. Okay. In our lab. So this you can see live stream of random hex numbers. Okay, so it's going to show true random number generated. Okay, in the quantum computer. This is true quantum random number generators. You can pull this into your Jupyter notebook using an API, and you can use this to create the cryptography if you want. Okay, there are a lot of projects around this. You know. You can have random colors generated for you. You can have random hex, I already showed you. You can have random binary numbers that you can use, sensing randomness of scatter plot. So you see, you continue to see this 256 by 256 pixel. So you can create this type of, this is alphanumeric block, so you continue to create one. And this is truly random. Unpredictable, okay, versus the other ones are predictable and that can be broken. So that being said, you can create a factorization algorithm. You start with a number of factors, then you start with a random number generator. It's a quantum random number generator. Then you put them through the modular exponentiation and a quantum Fourier transform and a quantum Fourier transform limit denominator, and then you do the extra square is available or not. If extra square root is not available, you pass it through the extra square root, filter out non-factors, and that's how you get your factor. This is through the quantum random number generator and a quantum computer, how you can generate Peter Shor's quantum computer. Okay, this is the Fourier transform, quantum Fourier transform. We'll go through it in a bit. A few minutes, we'll go through the quantum Fourier transform. How does it work? So this is how quantum Fourier transform work in the Quark software. And this is Professor Shor explaining the quantum Fourier transform and the Shor's algorithm and how he divides that. Okay, so we'll briefly go through his video and then we'll move to the IBM's quantum computer. These are the slides on cryptography. I'm not going to spend time on this. Okay, so let's listen to Professor Peter Shor, who, because of him, we are here talking about quantum computer because he brought quantum computer to industry applications. Okay, so let's listen to him. Just a second, okay.
I'll be talking about some recollections about when I discovered the factoring algorithm. But first, I thought we should go back and talk about where I was when this conference was being held. So when I was in 1981, I was a senior at Caltech, which is the same place Richard Feynman was. And so obviously, Feynman was preparing his keynote address when I was studying and getting ready to graduate, but I didn't hear anything about Feynman's keynote address or quantum computation. What I did hear from Feynman was a very interesting lecture that I went to called Negative Probability, and I'll mention it because first, he says a few things about negative probability in his keynote address, and second, I think it shows some, shed some light on Feynman. So in this lecture, Feynman said that, he was been looking at Bell's theorem, and Bell's theorem is this proof that Bell had that shows that the EPR paradox is unavoidable, that really quantum mechanics cannot be local and realistic. I won't tell you what realistic means, but that disturbed a number of physicists, apparently including Feynman. So he looked very carefully over all the hypotheses that went into Bell's theorem to see if there were any hidden assumptions that he could look at, and he found one. The hidden assumption was that all probabilities were between 0 and 1. So he asked himself, suppose we let the probabilities be any real numbers, less than 0 or bigger than 1, and we arrange things so that only when you add up the probabilities to get the probability of some observable event, it has to be between 0 and 1. So this was his idea. And he hadn't worked it out when he gave the talk. And apparently he never worked it out because he published a paper a few years later called Negative Probability. And the very interesting thing about this paper was that this motivation for this negative probability work was absent from the paper. He didn't mention anything about Bell's theorem. He mentioned as motivation, well, is there any way we can avoid these infinities that appear in renormalization? And that is, that's another big paradox of quantum mechanics that nobody has done anything about. So I think this shows, that Feynman was really careful cultivating his mystique. He didn't mention the original motivation in the paper because, it would have been clear that he had been wrong about this and that he wasn't able to resolve the paradox of Bell's theorem. So he found another motivation for this work, which didn't destroy this Feynman mystique of never making mistakes. And there's another interesting thing about that, too. It shows that Feynman didn't take his own advice. In 1964, at a set of lectures at MIT, he said, I'm going to tell you what nature behaves like. If you will simply admit that she does behave like this, you will find her a delightful, entrancing thing. But do not keep saying to yourself, if you can possibly avoid it, but how can it be like that? How can it be like that? Because you will get down the drain into a blind alley from which nobody has ever escaped. Nobody knows how it can be like that. But 15 years after he gave that lecture, he then disobeyed his words and started worrying about how could it be like that. And it was a blind alley, just like he predicted. Of course, maybe the advice he was giving wasn't to professors who were tenured, but for graduate students. I mean, the only graduate student I know about who did a lot of, had a successful thesis on the foundations of quantum mechanics and avoiding Bell's theorem is Hugh Everett, who proposed the many worlds theory in his graduate PhD thesis. And he left academia after he graduated. So now I want to skip ahead to the next time. The first time I heard about quantum computing, it was a talk that Charlie Bennett gave at Bell Labs. And I don't remember the exact dates, but it was obviously after Bell's theorem in 1986. And I think it must have been, or not Bell's theorem, it was after BB84 in 1984, but it must have been before Charlie built his QKD apparatus in 1991, because I don't remember the apparatus from the talk at all. Anyway, Charlie gave the BB84 key distribution protocol, and he asked an open question, which was, is there any way of proving mathematically that this is secure? So
this was the Peter Shore. You can watch his video on YouTube. He's quite good at what he talks about. So what we are going to do now, we are going to change gear and go to the last topic of the day. I mean, we can keep on going, right? But this is a trial class. We offer a full 2-day training in this topic, right? Over 2-day training, and I'm quite proud that most of the students who joined at 9 o'clock, they are still around at 11:15. So I'm quite proud of that nobody has left. So I'm able to keep you guys engaged. I'm recording this session. So what we're going to do is we are going to go into IBM's quantum experience. And we are going to do the IBM quantum experience. We're going to log into the IBM quantum experience. And we are going to log in and try to run a quantum computer, right? Submit a basic job on quantum computer, and get the API tokens and all the good stuff. Go into the lab, compose a quantum circuit. And this is one of the circuits that I had built in one of the classes I taught. And you can basically run a circuit here. These are the Ket0 2-qubit system. I put it through the Hadamard gate. It gets into superposition. Then I do the entanglement using the CNOT gate. And I measure, right? I measure the and this is the Bell state. The outcome of this can be seen here. I can view the details, how it was completed, this job was completed. And you see ideally, the outcome should be 0, 0, and 1, 1. But what we see here is there's a noise. There's a quantum noise here. That's the outcome of this, right? I can submit this again. And if I want to submit it, I can choose which one I want to submit it. So this one is IBM Q Manila, Bogota, IBM Santiago, Belém, Quito, Lima, Yorktown, Armonk, Stabilizer, MPS, State Vector, Simulator, and these are the computers, okay? So I'm gonna submit in one of them, which is not busy right now. So probably in the Bogota one, which has 5 qubits and 32 quantum volume. So this looks good, and I'm gonna run 1024 shots, and then now it's gonna queue my job here, and I can go to the job list of all the jobs that are running here, this is a few seconds ago. I can look at the details. I can share this, or This is already completed. July 31, 11:14 a.m. is completed, and these are the results. This is much better result than the previous one where the noise is minimum, and we are able to get the result of 0011 out of a very basic Bell state ZZ measurement where I'm doing a basic entanglement. This is a Quickscript code from Python code and Quickscript. This is a circuit. We have a quantum register, you have a classical register, and we are able to measure the two. We are putting the Hadamard gate here and C0 gate and measure both the qubits, okay? And this is the input and the output, phase angle, and so on, okay? This is a very basic circuit. You can put in a much more complex circuit. Here we have a lot more complex circuits that you can put it, and see how the results show up. Let's look at the composer, and these are all the circuits that I have submitted. This is the multi-mod 15 circuit. This is the first quantum circuit. This is superposition circuit. This is the Grover's example. You see Grover's example here. You have a standard GSZ. So different type of examples. Grover's example, we can look at that and submit it to see. We can set up and run Grover's example here in, again, Bogota. We can run this in Bogota, and you will see when it's complete what result we get, okay? What result we get. So now, a few seconds ago, I submitted the job, and job should be queued, running. It's running. The job is running already. So now you see this created, transpiling, validating in queue, running, and run. Okay, so you got a very good result. The result is 0, 0, right? Majority of the frequency is 0, and then you have the noise. Okay, this was the Grover's example. Okay, so you see the Grover circuit being built here, and this is Grover's example. So then, as I said earlier, there are several algorithms like Grover's algorithm, Dioché's algorithm, Shor's algorithm. There are several problems that needs to be solved. Okay, so this is the environment where you can submit a circuit like this. This is one of the most sophisticated environments, and you need to learn how to build this circuit. And I teach you in my course that is coming up in around 3 weeks. I have my 2-day training coming up in 3 weeks. So today is 31st. So my training is coming up on 14th of August. Okay, 14, 15 August. I'll have my training. Okay, sorry, not 14, 15, but 21, 22 August. So I'm gonna post the event later on, and I will also send you the video of this class later on. So you can start this. You can run this using a notebook also. So I was showing you this this slide here, and I had this Jupyter notebook that I had prepared. I can open this link here and run the program. Okay, I can run this program, and I'm able to get the results, right? So I'm gonna install some quantum random circuit, then install Qiskit, IBM Qiskit. I have this code I got this code from my IBM's quantum experience when I went here. I got my API token, so I'm going to use that token here instead of this one, and I'll be able to connect to my IBM's computer using this, right? So let's do this all over again. So I'm going to run this guy, initialize it, and then run the installation. And once I run the installation, I'll be able to go to the next step. I'm using Google's Colab, and I should be able to run the problem. Okay, so this is it. So So it's installing all these packages, the QRandom packages. It's installing all these packages here, and once the packages are installed, we can run and get some real quantum random numbers generated using the QMU slide I showed you. So that's it. It's complete. Now I'm going to create the two random numbers. You saw these are the two random numbers generated, 8 random numbers. I can put as many numbers I want through an API. Now I'm going to install the Qiskit and Qiskit random number generator. So it will install the package. It's installed. Now I'm going to connect to the IBM's quantum computer using the API token I got from IBM Quantum Experience and see how many backends are available. So you have the IBM Q, IBM Q main, IBM X2, Armonk, Santiago, Bogota, Lima, Belém, Quito, State Vector, MPS, Extended Stabilizer, and Manila. Okay, so these are all the machines that we saw in the user interface that I was showing you, right? So this was all the computers we are seeing in the Jupyter Notebook. Now I can say which one is the least busy quantum computer. So it's going to go and ping all these quantum computers and see this IBM QX2 is the least busy quantum computer. And I'm going to generate a quantum register like this, Q equal to quantum register 2, classical register 2, generate a quantum circuit between the quantum register Q and the classical register, and you are able to create a quantum circuit. And this is through a simulator, you are able to create a 1, 1, and 0, 0. This is a circuit I just showed you in the quantum experience, the Bell state circuit. I showed that to you earlier, right? The Bell state circuit. And this is what I have created in the Jupyter Notebook here, you see. And this is much little bit more complicated circuit. And this is, I'm applying, this was to a simulator. So you got 50-50. But when I apply to the real quantum computer, it takes a little bit time. Once the instructions are complete, you see there's a lot of noise in this. So ideal answer is this. But when you use a quantum computer, you have a lot of errors you need to correct. Now this is a quantum random number generator, running a quantum random number generator. It shows that here. And then you see the other circuits here and the Shor's algorithm factorization. You can see the factorization completed here, okay? So this is the example of how you can run it using Python and Qiskit, a circuit and a Shor's algorithm, okay? So this is something I wanted to show you. Now, last topic we're gonna go through is the Google's quantum computer. So I can go to the Google Circ, and Google Circ is the Google Quantum AI. And you can do a lot here in this quantum circ. They don't give access to the real quantum computer, but you can definitely run through these examples like variational algorithms, basics, approximate. You can do Rabi escalation, hidden linear function problem, Shor's algorithm, Dioche's algorithm, Bernstein-Vazirani algorithm, Belling inequality, noisy simulation, qubit placement, heat maps, and then Grover's algorithm. And then you can do a lot of advanced stuff also. And each of them have the Jupyter Notebook that you can run and run this. I go through all of them in our class. So this is how Google's quantum computer runs called Circ. You can even run AI algorithms through Google's quantum computer, but all of them are simulators. You're not able to access it, okay? So this is the Google's quantum computer, and there are specific way it works, okay? So now let's, next for 10-15 minutes, let's go over the cloud computing environment right now. So if you go to the AWS, Amazon Quantum, they have, you can start a quantum AWS quantum computer, and they have, that's not the one. Yeah, so this is the one you are talking about here, Amazon Quantum Solutions Lab, and you can start. These are the jobs. AWS Bracket. Okay, this is called Amazon Bracket, which is the experimental quantum computer. So let's look at
Quantum computing is an emerging and exciting field. It has the potential to solve computational problems that are beyond the reach of traditional or classical computers. In the future, quantum computing could transform areas such as chemistry, finance, drug discovery, and more. Researchers who want to experiment with quantum computing and develop quantum algorithms and applications unfortunately face numerous challenges. Getting access to different types of quantum computing hardware has been difficult. Running simulations of quantum computers can be expensive and complex, and development tools are often tied to individual technologies. Amazon Bracket overcomes these challenges by providing a fully managed quantum computing service in the cloud, so you can more easily explore and innovate in this emerging field. Amazon Bracket enables you to design and build quantum algorithms with technology-agnostic tools in your own development environment, or by using Bracket's managed notebooks. You can test and debug your code with local and on-demand high-performance simulators. Then, with Bracket, you can run your code on actual quantum computers, choosing between different quantum technologies from multiple providers, so you can decide which one best fits your applications. You can also build and test hybrid quantum algorithms, combining quantum hardware with the classical computing resources of the AWS cloud. Amazon Bracket's pre-built examples, tutorials, and tools will help you get started quickly. And our partners and consultants are here to support your journey. Step into the future with quantum computing and Amazon Bracket.
Okay, so you got an idea. So you can log into the quantum computer, Amazon Bracket, and once you log in, you'll be able to use it for your. I'm not going to log in right now, but you can use Amazon Quantum, this Amazon Bracket, and I think I can just use this. So you can, this will log me into the quantum processing. So you have all of these quantum computers available, like the D-Wave you looked at. We go through a lot of this Rigetti ones when we go through this. These are simulators, quantum simulators. IonQ is another company we haven't got through. We went to go through there. You have notebooks. You can start notebooks. You have tasks. It tracks everything, builds integrated, all of this. You can run the problems like similar to the one we ran in the D-Wave systems. The one I showed you, you can run here on this and push the logs into the AWS S3 or other systems. So basically you can have an app front end and have a quantum backend, and you'll be able to run it, okay? So this is quite interesting how it's set up, right? Same way you have, I already showed you the D-Wave, I showed you the Google, I showed you IBM. Other cloud that has similar environment, like Microsoft has Azure Quantum. I showed you a slide on that. Similarly, you can log in and send your load workload to Honeywell or IonQ or those computers, right? Microsoft is building topological qubits, which are very, very high quality qubits, but they are still in development, and everything is undercover at this point. But you won't be surprised Microsoft coming out with a surprise announcement sometime this year, looking at the development. Okay, So this is the AWS. I showed you the IBM, D-Wave, Microsoft, Google, all of them have it. Google doesn't give access to the machines. They just give simulator, but you can play around with the circ. And they have Google Quantum AI, where you can run like object detection, sentiment analysis, classifiers, and so on through a quantum computer. And it's able to run deep learning algorithms via quantum computer. I go through a deep dive into that in my training, two-day training. So you're most welcome to join me in my two-day training. I think I have covered everything I wanted to cover in this class. I hope it was beneficial to you and you were able to understand. I have enabled the chat. If you guys want to send some message, you can send now. And you can unmute yourself if you need to have some questions. You can answer. I can answer now. Okay. So if you have any questions, please let me know. Else we are done for the day. Okay. So thanks everyone. The events will be published here, so keep an eye on it. I will send you emails. Okay, and this is my website. I showed you my website. This is my website. Okay. So this is my website. So you're most welcome to send emails. Yeah, so I currently work out of the Seattle office of Microsoft. I'm a principal data science manager there. I work on security and enterprise and security and in the core operating system, mainly Windows operating system security, and also Edge and IoT operating system security. Host OS in Azure mainly, right? And I manage a large team of data scientists and software engineers. We build solutions for Azure and Azure Cloud and AI, security, and in general, all of the secure tools like Microsoft Defender and others. So mainly I work on the data science application of that on Windows telemetry and so on. So when is the full quantum computing course? So Prasad, the full quantum computing course is going to be in 3 weeks. So 21st of August, we'll have this 21st, 22nd of August. I'll be publishing the event and I'll be sending all of you an email, but you can always keep looking for it here on erudition.eventbrite.com. Okay. Again, thanks everyone. So this has been and my courses right now are focused on philanthropy. So all the funds that are collected through this gets donated to COVID relief in Asia, maybe India, Indonesia, different parts of Asia, So, so you're most welcome to join. Thank you, everyone. All right, take care. Bye. I will send the recording to you. Bye. Thanks, everyone.
Thank you.
Thank you.
Thank you.
Thank you.